Well, hello, lovely class. We are going to talk about E2 reactions today. And E1, but we're starting with E2. So, E2 reactions occur whenever you've got a strong base. So, I didn't mean to cross that out, I meant to underline it. So, a strong base would be, for example, these and these. If you have something from here, and I'm going to add one more example, we did it in class, or we will do it in class. It's this, it's called tert butoxide. It's a tert butyl group with an oxide group, so tert butoxide. If you have one of these three things, and we really rarely see this one, then it's going to occur via an E2 reaction. Okay. So if we have strong base and a strong nucleophile, remember that a strong nucleophile will cause an SN2 reaction as well. So it's going to depend on if it's primary, secondary, or tertiary. So if you have an alkyl halide that is primary, then it will occur via an SN2 reaction no matter what. Okay, and we'll talk about why. If you have something that is tertiary, it'll occur via an E2 reaction, because remember, tertiary things don't have SN2. And if it's secondary, it can be both. Okay, so if it's primary, it's SN2, if it's tertiary, it's E2, and if it's secondary, it'll be both. So you'll get two products. You'll get an SN2 product, and you'll also get an E2 product. Okay, let me show you what that looks like. So here we're starting, hopefully you agree, this is a secondary bromide. You follow to the carbon that it's attached to, and you see that it's attached to two other carbons. So we have a secondary alkyl halide. Okay, I'm going to go ahead and react it with one of these strong base, strong nucleophile things. OCH3, and it's got a negative charge. So you should already, because of the last chapter, have a strong idea that this is a strong nucleophile. It also happens to be a strong base. So we know the nucleophile sense, as a strong nucleophile, it's going to attack this carbon, that's going to pop off, and you're going to get this as a product. If you don't know that, then you need to go back and do SN2 reactions until you're very comfortable with this as a product. But we also, so this is the SN2, we're also going to have an E2 product. And that E2 product is going to look something like this. And with an E2 reaction, this we call our alpha carbon. Okay, so it's the carbon that's directly attached directly to the alkyl halide. I'm just going to write to the X. Okay. And then a beta carbon is directly attached to our alpha carbon. So the betas are the two in pink that I highlighted over here and here. These are our beta carbons. Okay. Those beta carbons, if they have hydrogens, depending on the situation, may or may not be up for grabs. So here's what's going to happen. This in the top one, it reacted as a nucleophile, and the bottom one is going to react as a base. Bases love acids. This would act as the acidic hydrogen. So what's going to happen is that the electrons on this oxygen are going to go ahead and grab the hydrogen, or it could have grabbed this. It's going to grab them off the beta hydrogens, and then the electrons that were attached to the hydrogen are going to come down here, become a double bond, and push this bromide off. Okay, I want you to, if this is your first time watching this and you didn't watch the extended lectures, go through and do this again and again before moving on. So what you get is this double bonded thing right there. Okay. Now the exact same thing could have happened to the hydrogen up here. Okay, so it could have grabbed the hydrogen, that could have popped down and popped a bromide off, or the bromine off, and you'd get the exact same product, just the double bond would be up here. So I'll show you. You would have gotten this, okay? But these two are the same, right? If I just turn this one this way, they're the same product. Okay. So let's go through some scenarios. If the alkyl halide is primary, that means it's going to require a strong base, but a poor nucleophile. Okay, so if you have an alcohol halide that you want to react via an SN2 reaction, or an E2 reaction, if you were to react it with a strong, the same thing that we just did here, then you're reacting with a strong base and a strong nucleophile. So a primary thing will only go via SN2. So you'll get, that's an SN2. That's not what you want. So if you wanted to react via an E2, then you have to use one of these three things, because anytime you use those, you'll get an E2 reaction. So let's go ahead and react it with our tert butoxide, which is probably actually the most common one. And let's see what we get. So the carbon that's directly attached to the alcohol halide, we call it our alpha. The one that's right next to it, that's attached to the alpha, we call our beta. There's only one beta. So there are two hydrogens on this beta. And just like before, the negative, the electrons are going to come over and grab a hydrogen. The electrons from that hydrogen will pop down, form a double bond, and that thing pops off. So our E2 reaction, you will get that. Okay. So the point of this is, if you want to force an E2 reaction, if you have a primary thing, you have to use one of these three things. Okay. I remember DBU as the darn bulky unit. And the reason that this happens is because these things are bulky. They're all really big, strong, big bases. Okay, and big bases can't quite get in to attach to this carbon like this one did. So here, these electrons attach to that carbon. But if it's something really big, it has a hard time getting around this big alkyl halide, this big halogen here. And so it can't attach. So the easiest thing for it to do is just grab a hydrogen that's a little farther away. And that's why you get this as a product. So big, bulky things that are strong bases can't attach, and therefore they'll react via E2. Okay, if the alkyl halide is secondary, unless you have a bulky base which cause only E2, the SN2 reaction will also occur. So just like we had up here, again, if you have something like this, if we reacted it via OCH3 negative, okay, we know already this is a secondary, this is a strong base and a strong nucleophile. This is this group right here, methoxide. Okay. And what you're going to get is both products. So you'll get the SN2 product and you'll get an E2 product. But if you react it again with something bulky, let's try that darn big unit, or darn bulky unit, you are going to get just the E2. Okay, so SN2, E2, here would be just E2. All right, but if it is tertiary, only E2 will occur. We know that tertiary alkyl halides cannot react via SN2. Okay, so if you react this, even if it's a strong base, and we'll go through this one a little more slowly just to make sure we're on the same page. If we react this with a strong base, if we identify this as the alpha carbon, all three of these are the betas. You really have this one, and this one, because they're all attached to this one alpha carbon here. So you got a beta, and a beta. They're all equivalent, they're all the exact same. Then what you're going to get is this will come in and grab a hydrogen off of one of these. So let's go ahead and just do this one. So it'll grab a hydrogen, this pops down, that pops off. Okay, that's always going to be the reaction of an E2. And I'll just kind of draw it the way it was drawn, even though it's a little funky. So you'll get something like that, okay, where this now is a double bond. This is that carbon, and this is the double bond. So this would be E2 only, once again, because this was tertiary. All right, let's keep it moving. Let's get into some nuances. So everything I provided you so far was relatively straightforward. Let's say we want to react And we're going to focus mostly on E2 from here on out. So I'm going to be using a lot of bulky bases to do that. So if we do something like this, remember, anytime you have this, it's E2 only. Let's talk about what this is going to give us. Now, here, you have your alpha carbon right here, the one that's directly attached. Remember, the betas are directly attached to the alphas. So you have 2 betas. Yours is going to choose the beta that's going to have a hydrogen pulled from it, assuming the hydrogen exists, is going to be from the one that's the most substituted. This one has 1, 2, 3 things on it, 3 carbons, and this one only has 2 carbons on it. Okay, so 3 carbons, and this one only has 2 carbons. It's going to choose this one. And that's because the more substituted a double bond is, the happier it is. So let me show you the example. So this is going to go ahead and grab that hydrogen. This pops down, that pops off, and you're going to get This methyl group is still there, and now you have a double bond right there. Okay. That's going to be our major product. Now it could still also do the other one. It could come over here, grab the hydrogen from here, that pops down, bromide pops off, and you'll have what's called a minor product. Meaning it just makes less of it. Okay, and here's why it ends up being kind of important. Here's kind of the difference between these. If you look at this one, if we circle kind of either side of the double bond on each of these, and ask yourself how many carbons come off of that double bond. Well, on this one, I have 1, 2, 3, right? So 3 things. So I just look to the dot and say, what's attached to that? And look to the other dot and say, what's attached to that? This has 2, this has 1, okay? This is what we call tri-substituted. Okay. This one has this one here and this one here on either side. It's only got 2. It's di-substituted. More substituted double bonds are going to be more stable. But if you always follow the rule of as long as there's a hydrogen attached to this thing, if you do that and grab the one that's on the most attached, if you look at your betas and grab the hydrogen on the one that has the most substituted stuff on there, that's going to be the one that works. Be careful, if this had been tetra-substituted, if I had another methyl group, there wouldn't have even been a hydrogen there to grab, so be careful about that. Otherwise, you'll end up with something with 5 bonds. Okay, let's do another one. So just to practice, and now would be a good time for you to pause it and see if you understand this concept. So here is our alpha. I just need to leave these uncapped. There's my alpha. Here are my 2 betas. Hopefully you agree, this beta has more stuff on it than this one. So this is the one we want. So that's got a hydrogen there. So if we react this with our tert butoxide, it's going to grab that hydrogen, that pops down, that pops off, and you get that as a product. That's going to be our major product. But if it happened to have grabbed off of this alpha here, it would have grabbed this, that pops down, that pops off, and you would have ended up with a double bond right there. And that would be our minor product. This one, I hope you agree, is more substituted. Again, you look to either side of the double bond and ask how many things are on it. This one I only have 1 carbon, this one I have 2. Same thing here. On this one I only have 1, and this one I only have 1. This is tri-substituted, that's di-substituted. Tri is going to be the major product. Okay, let's move on. Let's talk about stereochemistry, because stereochemistry does in fact matter. Particularly with which hydrogen we can grab. So let's say this is our reaction. Let's focus, well, actually, we'll do the major and minor product, I guess, here. So if we react this, we're just going to continue to do perturb butoxide because it always is going to give us the E2. Hopefully you agree. If this is our alpha, that this and this are our betas, right? This one's the more substituted, so this one should be the one we're interested in. Now, let's draw that hydrogen. If this one's on a dash, this methyl group is on a dash, this hydrogen has to be on a wedge, right? And that's good. And we'll talk about why here in a second. This, these electrons right here are going to come over and grab that hydrogen. That bond comes down here and it pops that bromide off. And, oops, I should draw it exactly the same. And you end up with that as your product. Notice, real quick, that this no longer has stereochemistry, right? The reason for that is it's trigonoplanar. Planar is in a plane, meaning there's nothing popping out or going back in. So this was an sp3 carbon. Here we have an sp2. So this methyl group right here was originally sp3 here. Now it's sp2. sp2 has no stereochemistry. Okay. We'd also get a minor product of, if this was our alpha, that's our beta, this also was a beta. So you'd also get a product of this, in which case this carbon still remained sp3, and therefore it would be a wedge. This is our major, this is our minor. All right, so some things to think about. This thing is bulky. This stuff is happening in 3D. This stuff actually happens. Like, so you can imagine if you have like a really big molecule trying to reach around some stuff and grab this. It doesn't want to be impeded by other things. Okay, so this bromide right here is huge. It's much bigger than it appears. So let's draw it like something like that, okay? This bulky group is like that. And it's got to reach around and grab this hydrogen. It can't come the same direction as this bromide is in, because if it comes directly in the same direction that bromide's in, they're going to bump heads. It can't grab it because this thing is too big. It's blocking it. And therefore, these things will only occur if they're what we call anti-periplanar. Anti-periplanar means one on wedge and one on dash. Or if we're talking about like a chair conformer, we're talking about one up, one down, for example. So if this were the hydrogen here and that's the bromide, this reaction could occur. But if the hydrogen was down along with that bromide, it couldn't occur. One up, one down, as an example. Okay, so let's go to this example. If you have something like this is a methyl group. If you need to draw, and I maybe should have done it, I've seen a lot of people kind of get these methyl groups confused with the hydrogen, but unless there's a hydrogen written, it's considered, it's carbon with this appropriate number of hydrogens on it. This would be the hydrogen here. So again, alpha, beta, this is the more substituted beta, okay? This thing and this thing are pointed in the same direction. So can this bulky thing go and grab this hydrogen? It cannot. This hydrogen is not anti-periplanar, so it's off limits. Okay, so your only product will be the minor product, where it grabs from this beta here, because one's on a dash and one's on a wedge. And it can grab that, and that can pop down, and that can pop off. And your only product that you're going to get is this. Okay? All right, what about stereochemistry on other things? So I think some books and some videos will go through and do a lot of Newman projections. It's kind of not so fun. So I'm going to try to be avoiding doing a lot of Newman projections and then rotating things around. We're just going to use our common knowledge and try to figure it out. So if we take this and react it with terbutoxide, we know this only causes an E2 reaction. This is a secondary alkyl halide. So if this is the alpha, so you follow the bromine to the carbon it's attached to, that's the alpha, then this one right here is the beta. That's the one we're going to be grabbing the hydrogen from. Okay, your question is, are these things in opposite directions? Are they in opposite planes? And the answer to this is yes, they are. One's pointed down and one's pointed up, and therefore this can grab that, that can pop down, that can pop off, and what we get is now this double bond. All the stereochemistry goes away because this was an sp3 carbon and this was an sp3 carbon. Now they're both sp2s because we have a double bond. So what you're going to get is this was an ethyl group down here. So that ethyl group, and this is actually kind of important, that ethyl group is going to remain where it is. And hopefully you agree, this methyl group and this methyl group were both on wedges, right? Let me write that in a better pen. If they're both on wedges, then they stay on the same side. They act like they're cis. Okay, so you'll get a methyl group there, and you'll also get a methyl group over here on this one, okay? And this ethyl group's alone because it was on a wedge, and then here we'd have a hydrogen that would be down here, which we don't have to write, of course. So when you're doing these double bonds, you wouldn't want to put a methyl group down here, for example, because if you put the methyl group down here, you're indicating that they're that they weren't originally wedges, or dashes, excuse me. So this and this have to be on the same side. Let's go ahead and do another example. And that would be a good time for you to pause and see if you understand it. Go ahead and react that thing with terbutoxide. All right, so from the top on this one, this is our alpha. So this is our beta. Okay, so this is the hydrogen that it's going to want to grab. These two things are in fact anti-periplanar. One's down, one's up, they're good. So this is going to grab this, that's going to pop down. That's not the hard part. We got a double bond, okay? So this and this, there's a double bond between our alpha and beta. Now we need to figure out which direction all these things go. Well, here we have a phenyl group on a wedge, or on a dash, and here we have one on a wedge, which means you'll have one here and one here. They're gonna be opposite. One was on a wedge, one was on a dash. If they'd both been on wedges, they'd both be on the same side, but they're not, okay? Wedge, dash, so they're gonna be on different sides. Then we have the methyl groups, the same exact thing. We have one on a dash down here, one on a wedge. But you wanna be paying attention if this one's on a dash and that one's on a dash, this and this are actually gonna be the ones that go together. So this is this methyl group, just in case that ever changes. So let's make it actually pink. I need my green, pink, and pink, okay? It's that carbon. And then this other carbon over here is going to be down here. Okay. And this phenyl group, which was pink, is this one right here. And this one, which was on a wedge, ends up, whoops, on a wedge down here. Why am I making it pink? I don't know. Purple. Let's make that sucker purple. Okay. So hopefully that makes sense. I put both purple ones on wedges, both pink ones on dashes, and they ended up on the same side of each other. All right. And if you can do this one, you're honestly in really good shape right now. Okay, so time for the next one, the E1 reactions. So for E1 reactions, that's when we're talking about a weak base. So let's go back to the very beginning weak bases and weak bases, these two situations here and here. Okay, for these two, I'm going to go back and go like this. Anytime you have a weak base and a strong nucleophile, SN2 is going to take over because strong nucleophile is what matters most. But when in situations where you have a weak base and a weak nucleophile, for secondary and tertiary alkyl halides, you'll get an SN1 and an E1. In fact, SN1 and E1 go together almost all the time. So an E1 reaction, if you'll remember, is when the leaving group leaves. The first step is always the leaving group leaves. So for example, the very first thing that would happen in this situation is that leaving group would leave, and you'd be left with a positive thing here. Okay, let's go ahead and react that with this. And again, the reason this happens only with secondary or tertiary is because only secondary or tertiary carbocations are stable. The positive charge is only stable if it's got 2 or 3 carbons surrounding it. So you already know what's going to happen with the SN1. If you don't, you need to go back and watch it and have this thing down. You should be getting OCH3 there. Again, this is a weak nuke and base, but you should have those memorized, I would say, before you even start doing this thing. All right, and now let's talk about the E2, or E1, excuse me. So this is the SN1. For your E1 reaction, very similar to what's already occurred, is the electrons on this oxygen are going to be the things that do the grabbing. This is our alpha carbon right there, the one that was on with the alkyl bromide. And these are our betas, okay? We have 2 hydrogens on each beta. It doesn't matter which one, this is a symmetrical molecule. So those are gonna grab that, that's gonna pop down there and satisfy that positive charge there. And you end up with that as your answer. Okay, very similar to E2. But there are some differences. So in this situation, let's go ahead and react it with a weak nuke, weak base. We know we get our SN1. Where we get this, and we get the OCH3 attached. Cool. And now let's talk about our E1. For our E1 reaction, the very first thing, again, that's going to happen is we lose that alkyl halide. That bromide takes off. And you're left with a positive charge there. Now we will eventually get into shifting positive charges. We'll realize that this positive charge actually shifts down here, but that's not for another 2 chapters. So we're just going to worry about what we know. And what we know is that this is our alpha, these are our betas, and we know that the hydrogen from the most substituted beta is the one that's going to be taken, just like with our E2 reactions. So those electrons come down, and those electrons go there and satisfy that positive charge. And we have this as our major product. Just like with E2, it could have also taken from these hydrogens, but those are less substituted, so we'll have a minor product. All right, moving on to this one. Now's a good time to pause and see if you understand it. Our SN2 reaction, it's pretty straightforward. We get that as our product. Our E2 reaction, sorry, and I'm reacting these all with HOCH3. With our E2 reaction, or E1 reaction, SN1, I'm going crazy. With our E1 reaction, again, we're doing E1 because this is a weak nuke and base. In case you missed it earlier, that's weak nuke, weak base. These are all SN1, E1. Again, the first step is that leaving group leaves. So we have a positive charge there. We have an alpha carbon here. We have two betas, here and here, right? Which one's going to be the major product? Hopefully you agree this beta has more stuff on it, so that's where the double bond's going to go between the alpha and the beta there and there. So you're going to get this as your product, and that's going to be your major. But it could also go between here and here, and that will be your minor. Awesome. All right, let's talk about stereochemistry. So if we react this with that, HOCH3, our SN1 product, hopefully you agree, that would stay the same, would be OCH3 and this. You get a racemic mixture, right, of both of them, because the leaving group left, and then that sucker could have attacked from front, or it could have attacked from back. It doesn't matter, because the first step was leaving group leaves. So let's talk about E1. When this leaves, you now have this. I should have drawn it the same way. I'm sorry. So this leaving group has left. Okay? Now you know, because this is a positive charge, if this is our alpha, and this one up here is our more substituted beta, that's the beta we're going to be looking at. This is also a beta for a minor product. You know that this one's on a wedge, or a dash, that's on a wedge. We can write CH3 if it helps you feel better. So this OCH3 is going to grab this hydrogen and have these electrons pop down. But my question to you is, did it matter if it was on a wedge or dash? It didn't, because it didn't have that big old bulky bromine getting in the way, which is why it mattered before. So now that you've taken that bromine away, you've taken away the circumstances by which it needed to go around. So it doesn't matter if it's on a wedge or on a dash. Anti-planar planar doesn't matter anymore. And that's what's kind of fun about the E1 reactions, in my opinion. They're straightforward, and you get this as your major product. It could have also grabbed the hydrogens down here and here, and you would have gotten a minor product of that. Major, minor. So that makes these other two really fun, whereas before they were kind of annoying, right? When this thing leaves, it can come from kind of any direction, right? So let's go ahead and react that. I'm going to react it with this, just so we're focused only on E1. This is a weak, bulky. I took our tert butoxide and I added a hydrogen to it. That took away the charge, and that always makes something weaker. So we got a weak, bulky base, so we're going to do E1 only. So the first step is that thing leaves. When that thing leaves, these things are now in a plane. Okay? So let me show you kind of what that looks like. You have a methyl group, and you have a hydrogen, and you have a positive charge. And this hydrogen, and this thing, and this ethyl group are still on their wedges and dashes. Okay? So in this situation, you're going to have, after your leaving group leaves, and these electrons, let's talk about which one it's going to grab. So this is our alpha, this is our beta, right? So this is the hydrogen it's going to grab. It doesn't have to be anti-paraplanar. It's totally cool. It can grab that hydrogen, and then these electrons can fall down. But while that happens, once this thing left, these were in a plane, and they could switch up and down. They could have been up here. They could have been down there. So stereochemistry no longer matters like it did before. If they're both on dashes, it doesn't matter. If they're both on wedges, it doesn't matter. You're going to get two products. You're going to get one where this methyl group was up and the ethyl group was down, and this methyl group was up. You would also get one where the methyl group is up, that ethyl group is down, and this methyl group was down. There's no real major or minor yet. We haven't talked about that. We'll eventually get to E's and Z's, but these are both going to be products because stereochemistry doesn't matter anymore. Once you've taken this bromide off and left it with carbocation, this could be here or it could rotate to here, and that's why it doesn't matter. They're in a plane, essentially. So now we have this one, same exact concept. So why don't you pause and see if you can figure out what the E1 product of this would be. So for an E1, I'm going to again use a bulky weak base. Hopefully you agree. And if you ever get stuck, you can do what I do, which is I draw two circles and I'm like, okay, that's my double bond. Okay, I know the bromide took off. I know I have a methyl group and a phenyl group. So let's start with the phenyl group up and the methyl group down. And over here, let's start with the phenyl group up. And this other methyl group down. And then let's draw the opposite. Keep one side the same, makes it easier. Phenyl group up, methyl group down. And over here, I'll do phenyl group down and methyl group up. And those would be both your products of an E1 reaction. All right, so that's pretty much it. That's every scenario I can think that you're going to encounter. And make sure you know the table right here, and you have a strong understanding of it, and that should get you pretty far. All right, crew, have a great day.